Hey there, how's it going? So in the previous video, we started to see how differential calculus will enable us to answer questions concerning the rate of change at a particular point on a function. So the example I gave was with a car taking off at the traffic lights, and we saw that the gradient of the tangent at that point will tell us the speed of the car that's read on the odometer. So what we're going to do now is start to look at how to actually calculate and find what the gradient of the tangent is on a function. So let's start with a function that's good to start these types of concepts with. Our trusty old parabola. All right, so we'll just have something like this. Y equals x squared. I'm just interested in the right half because we're going to take a point on the right half. So suppose we want to know, at say the x value of 1, we might want to know what is the slope or the gradient of the tangent at this particular point, right? So again, that will correspond, like in the previous video, to that would be the speed that the speedometer is reading on the car. So the problem here is to calculate the gradient we need 2 points, but we're only dealing with 1 point. All right. So well, if we don't have 2 points, let's just pick another one and see what happens. All right. So let's start by maybe picking a point a bit further along, maybe when x is 2, and then if we find the gradient of this purple line here, it would be a half decent approximation. All right. Okay, so we have that the gradient will say approximately equal to, well, for the purple point, back to 1, we've got the rise will be the difference of our function is 2 squared, the input squared. So we'll have 2 squared minus our putting 1 in, 1 squared, over then the run 2 minus 1. And so if we calculate this on the numerator, we're going to get 4 minus 1 is 3. And in the denominator, we're going to get 2 minus 1, which is 1. And 3 divided by 1 is 3. All right. So that might be an all right approximation. Like my graph's obviously freehanded, it's not to scale, but it's at least in the right kind of ballpark, right? It's a positive gradient. It's not 0 or negative, and this purple line looks steeper than the orange line, and so maybe the orange gradient is not quite as steep as 3, but around about there. All right, so what we could do to maybe improve our approximation is just pick another point which is a bit closer. So maybe let's say instead of putting 2 in, maybe we pick a point a bit closer to 1, say like bring it in halfway, 1.5. So what happens if we do 1.5 squared minus 1 squared on 1.5 minus 1, right? So just to clarify, this is the rise is the difference in the y coordinates, and so this y coordinate 1.5 squared is the output value from putting 1.5 into the function, minus 1 squared, so our 1 squared is going to stay the same because that's the point we're investigating, over the difference over to 1.5 would be the run 1.5 minus back to 1. Alright, so on the top we're going to get 1.5 squared is 15 squared with 2 decimal places, 2.25 minus this one's going to be 1, so we've got 1.25 over 1.5 minus 1 will be 0.5, and then 1.25 divided by a half is going to be times by 2 is 2.5. You could of course just put that in your calculator, but am doing this on purpose, so we'll kind of see something that emerges. All right, so moving our coordinate, right, our x coordinate a bit closer. 1.5 is closer to 1 than 2 is. Maybe our approximation has improved. All right, so it seems likely that 2.5 is closer to the actual gradient of that tangent line than 3 is. All right, so let's just go again and move even closer. So maybe let's not do halves, like let's go, start to just get some tiny decimal points, like if we say at 1.1. So we're now only 0.1 away rather than 0.5 away or 1 away. So the gradient is going to be maybe 1.1 squared minus 1 squared, which is of course 1, but that's the output minus the other output over the input minus the other input. All right, so 1.1 squared is 1.21, minus 1 is 0.21 over, that's going to be 0.1, and then 0.21 divided by a tenth will be times by 10 is 2.1. All right, so you can see as our point gets closer, right, the point that we've just chosen to approximate from is getting closer. It looks like this is going towards a certain number. Okay, so notice these numbers here. We've got 1, 0.5 and 0.1. So what do these numbers correspond to? Well, 1 here was the difference from 1, the point that we're actually investigated and that we're trying to find the gradient for. That is the distance to get to 2. 0.5 was when we considered 1.5, and 0.1 was the gap when we considered 1.1. Right? So what we kind of call this is the step size. Like imagine we're starting at 1. We start at 1 and we take a distance of 1. That's here. And when we have the gradient of that line, we end up with approximating the gradient of the tangent near 1 to be 3. And then when we take a smaller step, 0.5, we get 2.5. Then when we take an even smaller step, we get 0.1. And you could imagine you take an even smaller step again. Maybe if we did 0.01, you could try this yourself. If we went 0.01, then this will be 2.01 if you were to calculate it. So this we refer to as the gap from the point we're investigating and the little step that we're taking. We normally refer to that with h. Okay. So notice when h equals 1, we get that the gradient equals 3. When h equals 0.5, the gradient was 2.5. When h was 0.1, the gradient was 2.1. So it seems like as h keeps on decreasing and approaching 0, well, what could we say about the gradient? It looks like 3, 2.5, 2.1. As we keep reducing that step, the little that we're taking from 1, the gradient value is coming down and approaching 2. So that is in fact the gradient of the tangent at that point. On the curve y equals x squared, when x equals 1, the gradient is 2. Okay, now, just for the record, this line here that we've made is called a secant. So again, just like in the previous video I said, the language of tangent is connected to language of a circle, where a tangent line kind of, remember, goes in the same direction, skimming past one point on the circle. So likewise, a secant cuts through a circle at 2 points. So this is cutting through our curve at 2 points, our secant. So we can use the gradient of these secants by creating a smaller and smaller gap between the x coordinates that we choose to approximate the gradient of the tangent at that particular point. Okay, so what we can do, rather than having to calculate the gradient at one point and then another point, etc., and do a bunch of gradients of secants, and then look at the behavior, what's happening as we reduce the step size, we can kind of do that all in one go. So I'm going to do that again, but this time we'll just choose a different x coordinate to use. Right? So we'll still keep our basic parabola. Right, and this time I'm just going to choose to pick the point when x equals 2. Again, obviously this isn't the scale, but hopefully it's sufficient to be illustrative. Alright, so what I want to do now is frame the gradient of the tangent rather than with, actually picking a value for the step size, 1 and then 0.5 and 0.1. It's just we consider the step size as some arbitrary distance, right? So if we want to find our goal here, is we're now saying we want to find the gradient of this orange line here, right? This is our goal. Well, we can consider on the x-axis, we want to find the gradient of the tangent line to y equals x squared at the point where x equals 2. Well, let's consider taking a little step from 2, and that will be some distance h, right? So 2 plus whatever h is, so like 2 plus 1, 2 plus 0.5, 2 plus 0.1, etc. All right, so what are the output values going to be for these 2 points? So here, when x equals 2, if we input that into our function, we're going to get 2 squared. Now that's obviously 4, but I'm just going to keep it in this format intentionally. And then when we put 2 plus h into our function, right, this point, here, well, our function is x squared, so whatever we're inputting, we're going to square it, and our input is 2 plus h. All right. So now we can calculate the gradient in a similar way, but instead of with actually putting numbers in, we're going to have an algebraic expression with h in it. So exactly the same as what we did here, the gradient is going to be approximately equal to, well, the rise over the run between these 2 points. So the rise, the difference in the y coordinates, will be 2 plus h squared minus the 2 squared. And then the run is going to be the difference between the x coordinates. So the difference from here to here, which will be 2 plus h minus 2. So already we can see something that simplifies. 2 and minus 2 are going to cancel. And so we end up with h, the step size on the bottom, right? Which is what happened over here. The distance here we chose for that secant was a step size of 1. And then the distance I chose from 1, 1.5 and 1.1 were a distance of 0.5 and 0.1 respectively, and that's what ended up on the denominator as the step size. Okay, so let's keep going with this algebraic expression. So if we expand out our perfect square, we're going to have the first term squared, double the product, so 2h times 2 is 4h, plus the second term squared, and then we've still got our minus 2 squared up the top here, and then that's all over h. Okay, so again, some things cancel out. We've got a 2 squared minus 2 squared, right, which happens to be 4 minus 4, but This is called foreshadowing. All right, then on the top, we've got 4h plus h squared. So they've got a common factor of h. We've still got our denominator over h, but now that our fraction is factorized, we've got a common factor on h on the numerator and denominator we can divide throughout by. And so we find that the gradient of the tangent on the curve y equals x squared at the point where x equals 2 is going to be 4 plus whatever step size you take, right? You'll notice here that there's a bit of similarity with these. I said at the end of the day, we ended up with 2 is the actual gradient, and 2 plus a step size of 1 was 3. 2 plus a step size of 0.5 was 2.5. 2 plus a step size of 0.1 was 2.1. So likewise, if we chose a point a distance one away, so if we chose the point when x equals 3, well, 4 plus a step size of 1, we'd approximate the gradient to be 5. But then if we took a step that was smaller and closer to 4, like 0.1, if we did, to 2 rather, if we had 2 and 2 plus 0.1, then we'd get the gradient of the secant equals 4 plus 0.1 is 4.1. So, like over here, if we consider the behavior of what's happening as h approaches 0, well, the gradient will be approximately equal to 4 plus a step size for however big a step you take, and the gradient will actually equal what's called the limit as h approaches 0 of 4 plus h. So this is basically the concept of a limit, is what value is a certain algebraic expression approaching. Well, over here, the value of the gradient as h was approaching 0 was 2. Here, the gradient will be the value of 4 plus h as h approaches 0, and basically we can just find this by substituting in h equals 0. Okay, so the gradient over here is in fact the gradient of the tangent where x equals 2 on the curve y equals x squared has a value of 4. Alright, so like I made the little side comment about foreshadowing, this kind of calculation we could do for maybe when x equaled 3 instead. And the steps would be very similar. We'd end up with a different number here. And then we could take the limit. Now, we can't take the limit starting back here. Well, we can write the limit and write an equal sign there. But it's not appropriate to do the bit where we substitute in h equals 0 because we can't sub in 0 on a denominator of a fraction, right? So this is kind of the process that we're going to be leading to do differential calculus. Well, I mean, we're already doing differential calculus, but this is just for specific points at this point in time. But what this is going to build to is you might notice that there's a little bit of a pattern that's possibly starting to emerge. Particularly for this equation y equals x squared, we had that when the x coordinate was 1, we found that the gradient was 2. And again, just specifically for the graph y equals x squared, when the x coordinate was 2, we had that the gradient was 4. So maybe the pattern has got something to do with the particular x value. And it looks like when x equals 1, gradient equals 2, it's doubled. When x equals 2, the gradient equals 4, still seems like it's doubled. Right, so you could, for example, try out this procedure yourself for when x equals 3, and you'd anticipate that you might get 6. So since a pattern is emerging, it seems like for this function, there might actually be a pattern which we could frame as another function, which tells us the gradient at particular x values. So that's what we're going to be moving towards. Alrighty, that's it for this one then. Catch you later.